Salut and welcome to our presentation on decentralized collaborative state estimation for added inertial navigation. This approach should support our aim for 3D reconstruction in a GPS-denied environment with a group of communicating and collaborating microaerial vehicles. My name is Roland Jung and I'm a PhD candidate at the Karl Popper Colleague on Networked Autonomous Aerial Vehicles at the University of Klagenfurt. Assuming a swarm or group of communicating agents, each agent within the group maintains onboard an estimate of its pose with respect to a navigation frame. This estimation is performed within a versatile quaternion-based aerostate extended gamma filter using the inertial measurement unit as state propagation sensor. Besides the IMU pose, the IMU biases and calibration states of the camera and the vision frame are included in the state vector. The calibration state between the vision and navigation frame G allows a loosely coupled camera-based navigation, and we will see later that this choice allows agent to navigate with respect to a common navigation frame. Relying only on the IMU measurements, the local estimate would drift heavily due to different types of noises and biases within the IMU measurements. Therefore, we assume that agents are additionally equipped with a camera setup providing a metrically scaled relative pose with respect to the vision frame. For instance, a stereo camera or RGBD camera in combination with a SLAM or a visual odometry algorithm can be used. In our case, some agents might additionally receive absolute position information, for instance provided by a GPS sensor or a motion capture device. The agents can be seen as distributed estimators with a local state consisting of a mean and a covariance matrix. Therefore, the local states have to be treated as joint global state if they are correlated. In the beginning, agents are uncorrelated and therefore no cross-covariances in the joint covariance matrix exists. But joint observation between agents introduce cross-correlation between the local states. What is a joint observation? The idea of a joint observation is the following. One agent acts as interim master that gathers others agents' local states and performs a joint observation to correct them. A joint observation could be a relative pose between two agents, which is in our case obtained by overlapping camera views. The challenge in collaborative state estimation is the maintenance of the introduced cross-covariances, as those need to be considered. Otherwise, the estimators will be inconsistent. In a distributed setup, this would require a persistent all-to-all communication between agents and imposing a tremendous communication and processing effort. To overcome this burden, we use approximation provided by Luft in 2016 that requires communication only for processing joint updates. A relative pose observation between two agents' cameras, for instance based on overlapping camera views, allows us to eliminate one agent's navigation frame and to relate them to the same navigation frame during the first encounter. In our case, it is related to the agent with the low reference ID or the one that obtained already an absolute position update. This allows us to perform joint updates between cameras and that agents are navigating with respect to a common navigation frame. The re-initialization is based on compounding a pose chain including the uncertainties of the joints. A pose T between a coordinate reference frame A and a frame B is an element of the spatial Euclidean group. We define a distribution on a pose with its uncertainty using microlit theory introduced by Sola in 2018. This allows us to compute an absolute pose update using the local state and the relative transformation between agents' cameras. Second, we can compute the vision frame of agent 2 with respect to agent 1 in order to reinitialize it. We evaluated our algorithm on two different scenarios using two different real-world datasets for microaerial vehicles and visual inertial odometry. In the first scenario, we wanted to demonstrate that an agent only having an IMU can restore all 6 degrees of freedom by performing joint relative position updates with another agent that receives absolute position measurements. In the second scenario, all agents are navigating camera-based and one agent is additionally receiving absolute pose updates. Furthermore, relative pose updates were provided only on sufficient camera overlap between agents. In this scenario, we are especially interested in the behavior of Agent 2. Agent 2, with the green solid line representing the estimated trajectory, is drifting heavily due to wrongly initialized states until the first joint relative position update is performed. These relative position updates are indicated by an orange line and are performed at the rate of 10 Hz. We can clearly see that the estimated state is quickly converging towards the ground truth trajectory, represented by a dashed line, by just receiving corrections from joint observation with Agent 1. For the second scenario, we used 3 visual inertial odometry datasets and calculated the relative pose between cameras if the overlap of the camera frustra is greater than 40%. In this scenario, we want to demonstrate the strength of color-based state estimation using overlapping camera views. The relative pose update, indicated by an orange line, is based on sufficient camera overlap. To demonstrate the proposed reference scheme, the vision frames of the agents are initialized with an offset. Furthermore, the dataset suffers from missing ground truth information, leading to skipped measurement updates. This models the case of message drops and leads to drifting estimates. One can clearly see that the joint updates are immediately correcting agents' estimates and allows them to navigate with respect to a common reference frame. Summarized, we extended the quaternion-based aerostat extended gamma filter with color-based state estimation capabilities requiring communication only for joint observation. We proposed an initialization strategy that uses a pose chain to relate agent with respect to a common reference frame. The first evaluation shows that joint relative updates can be used to restore all 6 degrees of freedom on participating agents, while the second shows that our initialization strategy and the relative pose measurement model works under difficult and realistic conditions. Thank you very much for your attention.